Good evening, everybody, and welcome to Veritas Prep. I hope you had a fantastic Mother's Day weekend. I'm excited to be able to dive back in to this last week together. It really is hard to believe that we are already on our last week of class, but we're going to finish very strong. Thank you, each of you, for being here, as well as thank you in advance for all the contributions that you bring to the table when it comes to our discussions on the GMAT. A lot of the energy and excitement that we feel in class is in great measure due to you. So thank you for that. And of course, we would definitely be remiss if we didn't thank our incredible Jeff Yin. So thank you, Jeff, for being here with us as well. It's always phenomenal to have your genius on board behind the scenes and with us to help answer questions. Let's go ahead and dive right into today's class. Now, you remember, I like to have a little tradition, a little quote that has everything to do with what we're covering that day. This one is from Anonymous. Who's like, Anonymous sure has written a lot, if you think about it. When I first ran across this quote, it was attributed to what looked like a NASCAR driver. And of course, to be honest, I think this works very well for a NASCAR driver. But as I began to kind of dig into the history of this quote, I was able to discover that this quote precedes NASCAR by several decades. And the earliest time this ever shows up is a little blurb in kind of a trade magazine called the Pacific Printer back in 1920. But whoever said it, it definitely applies to what we're going to be doing this week. So Anonymous said, our business in life is not to get ahead of others, but to get ahead of ourselves, to break our own record, to outstrip our yesterday by our today, to do our work with more force and finer finish than ever. Now, you can see how, or why a NASCAR driver would say this, describing not to get ahead of others, but to get ahead of ourselves. But this certainly applies to the GMAT as well. Your business on the GMAT, in the end, is not necessarily to beat other people, but to beat your own records, to outstrip your yesterdays by your todays. And the way that you do it is do your work with more force and finer finish than ever. Of course, force implies like willpower almost, and finer finish implies smart, not just long or for a whole bunch of time. And this goes right back to the feedback loops pattern that we've been talking about throughout this entire class. Now, because of this quote, Jeff and I are going to do something a little bit different for our friendly GMAT Jiu-Jitsu challenge that we have each class. Since our business in this class is to help you get ahead of yourselves and not necessarily to get ahead of others, the way we're going to award our GMAT Jiu-Jitsu Master at the end of class today and next class is instead of just having Jeff count the raw number of kudos that he's given, Jeff has kept track of those kudos throughout the entire class. And in order to be able to become a GMAT Jiu-Jitsu Master today and next class, your job is to get ahead of yourself. So in the end, the way you're going to win this one is to beat your own averages. Which means if you haven't participated much in class, well, here's your opportunity to be able to easily take a quick lead in the GMAT Jiu-Jitsu Challenge. For those of you that have participated a great deal, to be honest, the reward will be your own GMAT performance anyway. But it's basically the challenge is to do even more, to continue that great energy and excitement that you've contributed to class already. So ready to go, let's dive into statistics and combinatorics. Now, stats and combinatorics is basically the mathematics behind Las Vegas. It's the mathematics of probability and the mathematics of arranging things in different orders. And if you master the material in this class, Oh, well, maybe your next job is to be able to go to Vegas and start doing some card counting. Of course, the more you understand the mathematics behind games of chance and different possibilities of arranging things, you'll come to discover that there's a really good reason why the casinos in Vegas are bright and shiny. But sometimes the people in the casinos aren't always quite that bright nor shiny. It's because the mathematics basically leads to an unescapable conclusion that the house always wins. So here is just kind of an overview of what we're going to be covering. It's basically three branches of mathematics that are connected to each other while simultaneously being independent. Statistics, combinatorics, and probability are three branches of mathematics that are designed to calculate real-life situations. Now, they're considered difficult by most students, but not because the math is actually difficult. They're considered difficult because you likely haven't covered them before. I've got kind of a funny confession to make at the beginning of this class. When I first took my GMAT, I had not studied combinatorics at all. I mean, I knew what the statistics were and I knew how to calculate probability, but in terms of combinatorics, this was new to me. I knew what a factorial was, but I didn't know how to calculate the different number of arrangements in a linear order with exceptions or something like that. No idea. And yet, you can imagine that I must have done really well on my quantitative portion, otherwise I would not be standing here as a Veritas Prep instructor. I do remember getting a few questions on my GMAT that dealt with combinatorics, and while I didn't understand the equation, I didn't know the equations for them, never studied them, never knew what they were, I was able to think my way through these questions. And really, remember, the GMAT's about critical thinking skills. After we set the foundations for these three branches of mathematics, these questions are actually made harder through reasoning, not necessarily advanced content knowledge. I was able to basically derive what the answers must be based off of the situations they gave me. Now, we're not going to have you at that disadvantage. I probably spent a little bit longer on questions than, to be honest, I should have spent had I known the basics of combinatorics. So we are going to give you the basics and we're going to give you the foundation and the equations, but we're also going to teach you how to think about it. And in the end, that's what the GMAT's all about. Now, hopefully, since last class, you had the chance to be able to get through the skill builder for stats and combinatorics. This is your last big one. And if you haven't had the chance, or if you find yourself in need of a little bit of a refresher, you can always refer back to the skill builder in the Stats and Combinatorics manual for a great the tutorial on these basic topics. We are going to cover a lot more content, kind of skill builder level in this lesson than we normally otherwise would, simply because it's new branches of mathematics. But you can always go back and do those drills to make sure you understand what's going on. Here's our plan of attack. It's basically a three-pronged approach. We're going to start with statistics, we're going to then take a break, dive into combinatorics, take our second break, and then we've got a really high probability of diving into probability in the end. So let's get started. Remember, all the way through the lessons, watch for the jiu-jitsu match between you and the writer of the test. There will be a few things the test is going to do today to try to break your balance. Watch for these. Basically, where it baits you into making assumptions that aren't accurate. On the other hand, you'll see a lot of leverage points. Many of these are kind of strategy level leverage points, where depending on the structure of the problem, it will basically tell you, you need to do this, or you need to be aware of that sort of thing. Of course, if you got the Stats and Combinatorics cheat sheet in front of you, you might already be familiar with this vocabulary. And today we're going to give you great opportunities to see these leverage points as well as the way the test attacks you in action. Let's begin with statistics. Ready? You almost can't begin a discussion on statistics without invoking the immortal Mark Twain, who once said, there are three kinds of lies. There are lies, there are lies, and there are statistics. Now, Mark Twain definitely had a wit about him, but behind every witticism lies at least a kernel of truth. And there's an enormous amount of truth in what Mark Twain just said here. Statistics have been used ever since politics were invented to be able to lie. Now, it's kind of a tricky thing because it's not that the numbers are wrong, but a lot of times the conclusions based off of those numbers are inaccurate. Now, you've seen this already when we've talked about critical reasoning. Remember the statistical stretches where they give you a number and then base a conclusion off it that's totally invalid just given the number that they have in front of you. It's not the number that's wrong, but it's the logic based off of it that causes problems. Well, because people make massive errors in judgment using statistics in business. I remember studying some cases as part of my MBA where there was some the initial statistics seemed to indicate that one business decision was a good idea until you crunch the numbers a little bit deeper and you began to realize that there's a reason why that company folded under shortly after trying that decision because they made a really bad decision based off statistics. There's a really good reason why it's on the GMAT. Now, since Mark Twain said there are 3 kinds of lies, we're going to talk about 5 statistics on the GMAT, from average all the way down to standard deviation. As we start into this section, I want you to focus on more than just the calculational aspect of statistics. Many statistics questions are very conceptual. In fact, many statistical measures would take an enormous amount of work to actually calculate it. And so the GMAT is baiting you, and it's kind of like a mythogynous version where they're baiting you into going, oh look, you've got to calculate this out to the bitter end. But if you can understand it conceptually, you can get to really quick answers, especially if you can recognize the patterns behind numbers and the concepts behind the rules. Let's begin with average. Now, the mean is the average. The average is the mean. And on average, the GMAT uses mean more than average, which is actually kind of mean, but they're completely synonymous with each other. Now, you know the equation for an average. It's a sum of the numbers in a set divided by the number of terms in that set. But this basic shape allows you to be able to analyze things at a rather powerful level if you know how to play the game. For example, just manipulating this equation a little bit allows you to be able to figure out the sum of a number of terms in a set if you just know the average and you know the number of terms. You don't have to know each individual piece. And this sum right here is often the kind of the mythogliness of average questions. They'll give you a whole bunch of things and get you thinking you got to do all the adding. And then eventually you're going to have to divide to figure something out. But if you can't understand the concept, you can do it without all of the math. So that's, you see on the problem categorization, I've termed some questions mean average questions. And basically what mean average questions are in my mind are questions that use the term average, but it's a little bit of mythogyness. They're getting you thinking you got to do it the long way around where you can look conceptually at it and get a quick answer. Let me give you an example of a beautiful question that leverages average to get to a fairly quick solution. Now, this problem doesn't say the word average anywhere in it. And yet, using the rules we just showed you on that last screen, you should be able to leverage average and find the answer really quick. Wow, looks like we've got people already putting in answers. So I'm going to step out of the way here. You've got 2 minutes to figure this one out. We'll see you in 2. Last few seconds to be able to get those answer choices in. Remember, you always have my invitation. If you need more time, just to ask for it. But if there's no invitations for more time, let's go ahead and dive into this question. This one is going to be a great one to be able to analyze. Jeff, let's go ahead and close the polling station. You can see we have 4 of the 5 answer choices represented. And each of the, and nobody picked answer choice A. Good job. Answer choice A is it's a total, almost a made-up answer. It's not even really connected. And so if you picked answer choice A, you really didn't read the problem or understand what was going on. But with B, C, D, and E, one of these is the right answer, and all of the others are gorgeous trap answers. Let's start out and the trap answers are based off of missing a little leverage word, a little devilish detail that's crucial information. First of all, let's begin with the leverage right here, sum. As soon as you see sum, your brain should go, wait a minute, I know an equation that deals with sum. If we're trying to paint our target, this is what we're going for. I know that the sum of a number of terms is equal to the average multiplied by the number of terms in a set. So now that we painted our target, if we can get these two pieces, then we can calculate the sum without actually having to add it all. I mean, you see it? That would be a lot of work. 650 all the way up to 750, adding those values together and then like figuring it out. It would take you all day. But here's your leverage. Now, why don't we start out with the average? What is the average for this set? This one should be pretty easy to be able to think about, and we're going to give kudos to the fastest reflexes. Oh my goodness, maybe we have to give kudos to the first few reflexes. I think people were typing it in before I even finished. Yes, 700 is the average of these terms, and this should make conceptual sense. I mean, first of all, just 650 plus 750, divide that by 2 is 700. Well, 652 and 748. Add those together, divided by 2. It's still 700. We have a ton of pairs of numbers then when you look at the average of those pairs, it all turns out to be 700. So our average is pretty easy to figure out. But so this isn't where people struggle. Where people struggle is right here. The number of terms in the set. Now, what are the number of terms in the set? Well, Elda, nicely done. Elda's even bringing in an equation. That's awesome. But notice we were seeing all sorts of different answers from 101 to 51 to 48, lots of different responses. And this is where the test is going to break your balance. There's some little devilish details up here that if you miss the question. But let's just start out with the devilish detail inclusive. Whenever it says inclusive, it talks about, you're basically talking about the ends, where you're including the ends of the set. And let's do a small little example, just over here. So the number of terms in a set 1 through 5. Well, obviously there's 5 numbers in this particular set. But notice what happens. If we were just to take the biggest number and subtract it from the smallest number, we would get 5 minus 1 is equal to 4. And there's more than 4 numbers in the set. We can just see it right there. This leads to a fundamental rule when you're trying to count numbers in a set. And Elda, great job even using an equation there. You need to add 1 to it. Megan also identified that exact issue. It's if you were to just take the extremes, the range, because it says inclusive, you're technically undercounting it by 1. You got to add 1 to it in order to be able to get there. Now, notice once you understand that, then you start seeing different answer choices. But there's another little devilish detail here that if you read it too quick, you miss what's going on. The word even. If it's even integers, that means we're skipping the odd ones. So we go 650, 652, 654, etc. Now, notice what happens. If if you forget even and you forget inclusive, then there's going to be 100 numbers. 700 times 100 turns out to be answer choice D. But that's not the right answer. If you saw the inclusive but forgot the even, well, now you know you're going to be adding 1 to it. And so you'd go 101. 101 times 700 is E. But that's not the right answer either. If you realized it was even, but you forgot inclusive, then you'd realize, all right, there's not 100 numbers, there's 50 numbers. You do 700 times 50, pick answer choice B, and once again, you would have the wrong answer. In the end, though, you combine the even, which would normally make it 50, but because we're including the ends, we've got to add 1 to get there. 700 times 51 is answer choice C. Now, nicely done. Those of you that spotted that, looks like that was a fairly rare response. We only had 4 of you get that one right. So definitely pat yourselves on the back if you got that one right. If you missed it, again, congratulations, you did make this mistake on the GMAT. But you might want to make a little note about the importance of leverage words such as inclusive or words such as even numbers in a range, which is going to limit the number of terms in a set. I guess probably the biggest takeaway would be, hey, slow down when you're reading the question. Make sure you know the leverage of each of the pieces, and that's how you get there. Any follow-up questions on this one? Let's go ahead and try another one then. 2 minutes should get you there for this one as well. Now this is going to use the word average in there, so immediately you can start thinking about leveraging that equation that we gave you. This is another problem where you will never be able to know all of the numbers in the sum, but that's okay. If you can figure out how the pieces of the equation are related to each other, you can get to this answer fairly rapidly. So, 2 minutes, let's reset the polling station. We'll see what you can do. How are we doing on this problem? I'm still seeing several that have not yet put in answers. Would anyone like a little bit more time on this? Travis, thank you for asking. And Catherine, thank you as well. We'll have Travis and Catherine be our pacers. So as soon as you finish, let us know in the classroom chat. Everybody else, if you've got an answer, double check it. This one has as a massive trap, and I'm seeing several that have put in answers that have fallen for this exact trap. You've got a great opportunity to be able to kind of review what just happened. Fantastic. Thank you, Catherine and Travis. Jeff, let's go ahead and close the polling station. You can see the majority of the people that are putting in answers are picking either D or E. One of these is the right answer. The other is a massive trap. So let's talk about how you might have fallen for this trap, as well as the critical thinking skills you could have used that would have caused you to avoid this. First of all, you can see that we've got an average of 5 numbers is 6.8. Well, the sum of those numbers is pretty easy to figure out. I mean, after all, the sum of those would be 6.8 times 5. Now, here's going to be kind of a funny recommendation. Don't do this problem. Don't multiply by 5. Okay? Multiply by 10 and then divide by 2. That's actually going to get us there quicker. I mean, think about this. Multiplying by 10 is a piece of cake. You just shift the decimal over. So 6.8 turns into 68. You don't have to worry about the decimal multiplication. Then you can divide that by 2. And you can see the original sum is going to be equal to 34. Well, notice we're now going to take one of those numbers in the sum and multiply that by 3. And notice the other numbers are staying the same. And so the original sum is going to have some chunk. And why don't I just call the chunk C, okay? But then we're going to have the chunk of 4 numbers, and then we're going to add a 5th number to it. I'll just do C sub 4. Now, that's a very descriptive variable. The chunk of 4 numbers plus the number is equal to the sum. And now what's going to happen is we're going to take that, take that last number. We don't know what it is, but we're going to multiply that number by 3. And then it says the average is going to change. So still a sum, but it's going to turn out to be 9.2 times still 5 numbers. And once again, don't multiply that by 5. Multiply it by 10, divide by 2. So 92 divided by 2 turns out to be 46. And you can see it changes the actual sum by 12. I'm just going to do this, okay? Now, here's where the trap comes in. You might have looked at that and went, wait a minute, I'm going for which of the 5 numbers? So in other words, our target is what's n? What's that number that we just multiplied by 3? And what people sometimes do is they'll go, all right, well, since we multiplied a number by 3 and it changed by 12, we divide it by 3 and we have the original number. And that's where many of you might have actually fallen into the trap. 12 divided by 3, of course, is equal to 4. Then you pick answer choice D. But why can't we just divide 12 by 3 and get our value? Do you see it? Yes, Michelle, great catch. In the end, it would eliminate the original number. Notice the change between 34 and 46 is 12. But the change between n and 3n is actually 2n. Sure, we multiplied n by 3 to get to the new value, but the original value was included in the original sum, and we can't forget that. So in the end, the change is 2n is equal to 12. Divide 12 by 2, and you've got your actual answer. It turns out to be E. You can totally tell that GMAT's selling the wrong answer here. But multiply by 3 is not the same thing as add 12. You don't remove it and replace it with 12. You add 12 to x. So you definitely need to be reading carefully here. Now, I also want to draw your attention to something that if you, to be honest, if you picked answer choice D, my guess is you never did this right here. Your brain went, okay, sum, I know how to get a sum, and you never kind of wrote out what actually is going into the sum. Notice we don't have any we don't know the values for 4 of the numbers at all, and we never need to do that. But this is one of those mean average questions that bait you into thinking you got to know all the values. You don't. You can chunkify it just like we did here, but just by writing it out and going, oh, okay, this is chunk plus a number, this is chunk plus 3 times the number, and you're never going to make this mistake again. Sydney, interesting insight there. So Sydney's saying that we have a change of 6, and it says, Sydney said, so it's like the new value is 300% of the old value. Yes, a 300% of is different than 300% increase. Think about the difference between a percent of and a percentage increase, and people fall for that all the time. And if you're still struggling with the percents versus percentage increase, you can always go back to the arithmetic manual and just review those basic principles. Great catch, Sydney. All right. Now, let's talk about some great conceptual ways of understanding the concept of average. GMAT loves to use these. First, adding the average of a set of numbers to a set of numbers doesn't change the average. If you've got a bucket of numbers whose average is 5, well, if you're to throw a 5 into the bucket, adding an extra number, that doesn't change the average. If anything, it makes the average more 5 than it was before. In other words, it weights that average even more. Next, the average of an evenly spaced set. Now, this is a very common pattern you see in the exam. Just think about that last question, or the first question we did today, the 650 through 750, the even numbers from those values to those values. Well, the average of an evenly spaced set, you can calculate in 2 ways. First, it's equal to the set's median, but it's also the average of the largest and the smallest values. That's one way that we got to the average of 700 there. Now, next, shifting the average. A lot of times the GMAT will require you to kind of use both of these ideas. Sometimes they might give you a set that's not evenly spaced, but it's close. There might be one number that's off, so it's not necessarily evenly spaced, but still adding everything up is going to take a lot of time. But if you can realize, hey, we're really close to this, and pretend it's evenly spaced, you're almost guaranteed that one of the answers will be the evenly spaced value, and you know that can't be it. But you know, all right, if you got that one number that's off by a bit, well, you can approximate the effect that that number has. It's going to be shifted towards that number naturally. This is what we call shifting the average. Now, we also have some minor statistics. We'll cover the basic definitions here, and I'd like to do just maybe a couple questions just to make sure you got these down. But these do not show up as often on the GMAT as average does. These are median, mode, and range. Median is the middle value of a set of numbers, and the numbers must be arranged in ascending order. So if they're not arranged in ascending order, that's your first item of business. Let's do an example here. So let's say 2, 3, 5, 7, and 11. All right. Well, the median value of that set of numbers is going to be 5. Basically, you count your way in there, count your way in there. 5 is the middle value. Now, this works if you've got an odd number of terms. If you've got an even number of terms, let's say just take out that 11 right there, then you can still figure out the median, but the median is going to be midway between the two middle numbers. So in this case, the median is going to be equal to 4, the average of the two middle terms. Notice the median can sometimes be in the set if the set is odd, or it can be in between numbers, so it's not in the set. But basically the median is the boundary line that sets half of the numbers on one side and the other half of the numbers on the other side. Next is mode. A mode is the most frequently occurring number in a set. Now, this generally shows up if you've got multiple values that are the same. If we got a couple of 2s in that bucket of numbers, well, the mode is 2. Let's say we've got a couple of 2s and a couple of 7s. Well, the mode is 2 and 7. The tricky thing behind mode is there can be more than one mode. And basically, notice, if we don't have any extras, if it's just 2, 3, 5, and then 7, well, then technically they're all modes. They're all equally occurring in the set. Now, last is the range. Range is the greatest value minus the least value. Range is an awful lot like distance. You can go 3 miles west, you can go 3 miles east, but you can't go negative 3 miles east. Range can never be negative. Do you see it? Because it'll always be the biggest value, whatever it is, minus the least value. Let's do a little data sufficiency question that I just want to make sure you've got the concept of median down. In this case, we've got a set. In other words, just a bucket of numbers that's created by combining all the terms of buckets A, B, and C. So we've got some big bucket there, and we've just put A, B, and C into them. Says we haven't added any other numbers, it's just A, B, and C, and then asks what is the median, okay? So I'm just going to go like this. The median of D, there's painting my target so I know what I'm going for. Now, remember, a median is the middle value, the boundary line between the left side and the right-hand side in terms of numbers. And why don't we start with the low-hanging fruit here? I would argue that statement number 2 is easier. And the reason why is because it doesn't give us any values. We need a numerical value for this. And so statement number 2 just saying, hey, look, all of those buckets of numbers A, B, and C have the same number of terms in them. That's not helpful because if we need a numerical number, this is a specific value question, we need something to go off of. It's very easy to eliminate statement number 2, and therefore we get rid of the bottom statement and we get rid of both B and D. By the way, how many of you are using the data sufficiency arrows in your homework? And is that helping you to be able to eliminate responsibly, I guess would be a good way to say this, and as well as focus in on your strategy. I cannot emphasize this enough. Michelle, thank you, absolutely. I know Jeff has even introduced the data sufficiency arrow to the students that he tutors. That is part of the live online hours, the classroom hours that are available to all of the students. You get someone logging in, hasn't even been with us, and everybody finds this a very useful way just to think about data sufficiency. Awesome. So Travis, interesting. So, did you take another class before this one? I will tell you, Travis, if you have, there might be some bad habits. You must unlearn what you have learned. Oh, okay, awesome, Travis. Yeah. Kaplan is a great resource for questions. If you just need extra questions, but sometimes their strategies really leave a lot to be desired. Kaplan is a phenomenal company when it comes to preparing people for content level tests. The problem is that's not what the GMAT is. Flashcards will definitely help your content, but it could actually cause problems a little bit for strategic thinking. And Travis, and kudos to you. Thank you for sharing that. It helps us to be able to kind of have this conversation. I have had numerous students throughout the years that have taken courses from other companies, including and almost especially Kaplan, that they took it and they really didn't see large score increases. So it's useful to be able to talk about that. If you've got questions about anything that you've learned, let's talk, and then we can definitely help you get up to speed. Thanks, Travis. Okay. Yeah, isn't 1, 2, 10? Am I remembering right? It's like first, second, together, either, neither. Is that what it is? Yes. Okay. Yeah. To be honest, it's an interesting way to know what the answers are, but it doesn't really do a good way of strategically focusing in on the things that matter. Awesome. Thanks, Travis. Okay. So we've gotten rid of the bottom statement, and therefore B and D is gone. Now we look at the top one. It says sets A, B, and C have a median of 125. Now, statement number 2 is obviously insufficient. But remember, we can play the why are you here game. Doesn't matter that they have the same number of terms. And so maybe we could just come up with some specific examples that follow these rules. So we've got a median of 125. Well, let's pretend that they can have different number of terms. In other words, where statement number 2 doesn't matter, that knowing this isn't helpful. Well, let's say we've got an odd number of terms. Odd number of terms, the number's right there. So 125 is going to be there. And you can have other values on either side. Now remember, with median, it's not the spacing of it that really matters. For example, if we've got an even number of terms, so long as the median is midway between the two middle values, you can have the outliers being anything they want to be. I mean, this 200 could just as likely be 2,000, and that would be okay. We still have half the numbers on one side, half the numbers on the other. And you realize that the number of terms doesn't matter. So you should come up with an example and you go, wait a minute, if all 3 of those sets have the same median, that means you put all the numbers in the bucket, and you're always going to have half of the numbers on one side of that boundary and the other half of the numbers on the other side of the boundary. So statement number 2 helps us to test that theory and go, wait a minute, it doesn't matter if they all have the same median, then we have a half and half division no matter what, and the median of the total set doesn't change. As a result, we've got answer choice A. Then we talked about the why are you here leverage, the low-hanging fruit, easy numbers turning the abstract into something concrete, as well as a little bit of statistical smoke screens. We don't know what the numbers are. We don't have to. We're just looking for the conceptual approach that gets us to this answer. Any follow-up questions on this one? Okay. You'll also see what I've done over the last couple of questions. A lot of number properties and conceptual thinking can seem kind of abstract. And so what I sometimes like to do is, instead of trying to memorize all of the potential rules, is I just set up an example of what it might look like. Now, naturally, you do need to be careful that you don't embed assumptions into your concrete visualization of what's going on. But so long as you're careful and you're not embedding assumptions, you can turn the abstract into concrete, coming up with very quick, like almost reinforcing of the rules. Really, to be honest, trying to memorize that if you combine the sets of 3 different sets and they all have the same median, that the combined set will also have the same median, yeah, that's a rule you're never going to see again. This is making sense. So memorizing your way through the test isn't going to get you there. But visualizing your way through the test and double checking your assumptions that is the upper level critical thinking strategy for these. Okay, let's do this problem together. Can we? I just want to make sure you've got these down. This says, which of the following could be the range of the following set? Get us started. What do you see? Excellent. Great job. You're exactly right. Remember, there's no such thing as a negative range. So negative 54 isn't an option. And therefore, Michelle, great job. All of a sudden, A and E are out there. And Sam, kudos to you for that question. I love it. Sam asked, does this mean that X, Y, and Z need to be larger than 23? The answer to that, Sam, is no. They do not need to be. This is one of the big ways the GMAT is going to break your balance when it comes to set of numbers. I'm borrowing from a tennis metaphor here. I like to call this game, set, match. And the game, actually, I think isn't it volleyball metaphor too? Is that the same idea, game, set, match? But the basic idea is the GMAT loves to play a game with sets. And the game that it plays with the sets is it baits you into matching the order that it gives you those numbers with the actual order of the values, especially when we have variables. Now, obviously, if a problem says these are in order of increasing size, then yes. But if it doesn't explicitly state that, there is no convention for sets that requires the numbers to be put into the bucket in order of increasing size. So Sam, X, Y, and Z can be anywhere that they want to be. They could be in between -1 and 23. They could be equal to -23 or -21. You could have someone on one side, some in the middle, some bigger. They could be they could be larger. They could be the same value. You can't make any assumptions based off of where you put them in. Once again, unless the test says so. That is the concept of game, set, match. Now, many of you caught this as well. Great job. You saw we have some abstract values, but we do have some concrete ones. And if we're going for which of the following could be the range, notice we try to break could be. There's multiple possible ranges that could happen, so we can eliminate the ones that just can't be. Statement number 1 we can eliminate because there's no such thing as negative ranges, and we're already down to a 1 of 3. Well, if the numbers were in between, or maybe equal to 23, again, that could work too, then it would be a 23 minus a minus 21. In this case, 23 minus a minus would turn out to be adding, or 44. Now, 44 is a possible range, but it can never get smaller than that. And so X, Y, and Z, wherever they are, so we'll either increase it above the 44 or it will keep it the same. So in the end, statement number 2 also doesn't work because it's too tiny. The 23 and the minus 21 make it so statement number 2 doesn't work. And interestingly enough, we don't even need to evaluate statement number 3 because we're down to one answer since 40 is too small and minus 54 is negative. So 63 certainly works and we're done. We've got our answer. Now, I'm going to think like the test maker a little bit. It's time to anticipate what the test maker could do here to add maybe an extra level of complexity and break the test taker's balance even more. For me, to be honest, that 40 right there is seems way it works, but I would love instead of 40 to put 44. And the reason why I would, if I were the writer of the test doing 44, is because that really plays into that concept of game, set, match. It's that people go, oh no, X, Y, and Z's got to be greater than 23, so 44 isn't an option. Whereas if we were to restructure this problem, then the answer would be D. 2 and 3 work because 44 still could be a possible option. The problem never says X, Y, and Z are greater than 23, so don't make that assumption. Make sense? Great question. All right, last but not least is standard deviation. Now, here is the equation for standard deviation. And if we've got any of you that are twitching uncontrollably and spasming on the floor after seeing this, get back up, dust yourselves off, you're good. You are not going to use this equation. But you can see standard deviation is basically the poster child for ugliness. In order to actually calculate it, there is an inordinate amount of work that goes into it. And now I have included the steps for how to calculate standard deviation on the cheat sheet packet, just because I had a little corner that I wanted to put something in. It might help people to understand things at a basic level, but really in the end, can you see how you never will need to calculate standard deviation, actually calculate it? If any of you have taken a statistics class and the test or the writer of that curriculum required you to do calculate standard deviation by hand, to be honest, that person is a sadist. There's no reason to do that. And yes, Brad, that's exactly why. Seriously, you're getting your MBAs. If you need standard deviation, you're going to open up an Excel spreadsheet, hit equals STDEV left parentheses, and you're going to get standard deviation. And that's all you never need to worry about it. The GMAT gets this. Yeah, Michelle, I'm so sorry. Your teacher had you do that. That's busy work. And really, you've got to understand standard deviation conceptually more than anything else. Yeah, my condolences, Michelle. I'm sorry that you had to do it the long way around. So let's talk about why standard deviation is on the exam. It is a fantastic statistic that will get thrown around at you when you get your MBAs and beyond. So you've got to know what it means, but you also need to understand what it doesn't mean. First, on the GMAT, you should never actually have to calculate standard deviation. Now, I'm not saying that the test won't ask you for it. Sometimes that happens. Every once in a while, they're like, what is the standard deviation of? And it will give you a set of numbers. But remember, there must be a quicker, holistic way of looking at such questions because, dang, I mean, that's just a lot of work. And so here is my approximation for standard deviation. For you math lovers out there, you might take exception at this. This is more of an approximal or more of a kind of a definition hack of what it is. But for all practical purposes, it's good enough. Standard deviation is the average distance from the average. Now, I actually have reviewed this definition. If you're to try to calculate the standard deviation using this exact thing, you're generally going to be off by about a square root of 2 to square root of 3 for evenly spaced sets. But to be honest, it's okay. This is the basic idea. It's an average distance from an average, the average separation. In other words, how close the terms are spread around a set's average. And any problem that you need to calculate standard deviation, this will get you there more than adequately. Now, you'll notice because distance can never be negative. Remember, you can't go negative 3 miles west. Therefore, standard deviation, since it's the average distance, well, since you can't have negative numbers in that, then you're never going to have a negative standard deviation. It can also be never greater than half the set's range. Now, let's visualize this so you can see why. Let's say in our number line, we have a whole bunch of numbers that are just basically all right there, and then a whole bunch of numbers that are basically right there. The average is going to be midway between. And notice, though, the average distance from the average, okay? Well, a whole bunch of distances that are that far away, and a whole bunch of distances that are that far away. And so the average distance will be half the set's range. But as soon as you get another number right there, for example, then that separation or distance from the average is going to be smaller than the distances of the extremes. So you get a number in between that, and it's going to shrink the standard deviation. It will be smaller than half the set's range. And for equally spaced sets of the same size, in other words, the same number of terms, the larger the set's range, the larger the standard deviation. Range, because range is a measure of separation, and standard deviation is a measure of separation, these two things are related to each other. They're not the same thing, but sometimes it allows you to be able to just kind of see what's going on. Let's do another problem, and I want to do this one together. Okay? Go ahead and take a look at it. Read it on your own. As soon as you see a way to strategically tackle this question, type it in. Teach us. This one is a 30-second question if you can figure out what's going on. Excellent, Michelle. It's like negative 1.5 and negative 2. Those aren't options. There's no such thing as a negative standard deviation. And we are down to 3. Now, we've got a couple people saying can't be 0. I would argue the standard deviation can be 0. That is a possibility. However, think about our definition. Yes, Juan, great insight. In order for standard deviation to be 0, you'd have to have a bucket of numbers that are all the same. Just for example, just a bucket of fives. In a bucket of fives, the average is 5. The average distance from each of those numbers and 5 is 0. So the standard deviation there would be 0. So this is a physical possibility. But man, you look up at that set, and as soon as you realize we've got different numbers here, 0 is no longer on the table. And therefore, answer choice E, none of the above, must be the right answer. That's all we've got. Now, the GMAT is playing a little bit game, set, match here too, but that really doesn't come into play here. That just is baiting you to kind of overthink it. It's saying M is negative, and it does put M here between -3 and 0, but it doesn't have to be. This could be negative 2 billion for all we know. We're not sure on that one. Your brain goes, oh look, it's mirrored, that must be 1. Oh look, it's mirrored, it must be -5. But who says it's mirrored in the first place? As soon as you start inserting extra information into this problem, you've lost sight of what the problem is even asking. We're just going, which of them could be standard deviations? So we're playing the logical opposites game. We're eliminating things that can't be. And we eliminated all of them. No reason to actually calculate it. There's technically no way to calculate it because we do have variables. Okay, let's try another one. And I'd like you to give this one a shot. Read this one carefully. You've got 2 minutes to figure this one out. And once again, if you need more time, it's okay to ask for more time as we get closer. But 2 minutes should get many of you there. Let's see what you can do. Let's play the game. Excellent job. Now, let's visualize what's happening here. I see all 5 answer choices represented in our polling station. So this one we might want to really slow down and talk about this. But we're taking 100 and we're throwing him into 3 different buckets. But notice the actual, what it's actually asking for, kind of the target we're trying to paint. We're changing the standard deviation. And you can see if we were to actually do this math, this would take you all day because you would have to calculate we're going for how would it change? In other words, an increase in their standard deviation from largest to smallest, which means mathematically we would have to calculate the standard deviation of each of these sets, then throw 100 into it and recalculate the standard deviation for these entirely new sets, then subtract the different standard deviations and then come up with the value. That is mathugliness. When you see mathugliness, don't panic, party. There's got to be a conceptual way to look at it. Now, just visualize what's happening here. If you were to plug 100 into the first bucket, okay, 100 is naturally within the range of these numbers. It's actually close to the average separation from the average. Now, see if you can kind of spot this. These are evenly spaced sets. So the average is going to be the middle value. And notice, if we're going the average separation from the average, we're talking about 0 and 20 and 20 and 40 and 40. Well, a couple 20s, a couple 40s, and a 0. You're talking about somewhere around just maybe a little bit less than 30 or so. Make sense? Well, 100 is going to be 30 away from the original average. Answer choice A is not going to change this. You're not going to see a large change in standard deviation. But B and C, you're going to see much bigger ones. After all, both B and C, you're changing the range of the set, and therefore increasing by quite a bit the separation. Now, I would actually argue that it would be mean to try to figure out which one creates a larger change in standard deviation, either B or C. And the reason why is this. Add 100 into each of these buckets. You should notice that the average separation from the average for original bucket C is tighter. We have 0, 5, 5, 10, 10. Okay? Whereas B is 0, 10, 10, 20, 20. So B is a larger standard deviation naturally, but you plug 100 into it, and a larger standard deviation will create a larger change. This one's farther away from the average. But a smaller standard deviation will create a smaller, and you add 100 into it, this one's closer to that average. We have a smaller change with a smaller standard deviation. There's no easy way to be able to figure that one out, but you don't have to. Look out below. Conceptually speaking, it should be very obvious that plugging 100 into into A is not going to change the standard deviation by much at all. And this says from largest to smallest change. In other words, A is going to have the smallest change. There's only one answer choice that has A as the smallest. And so you don't even need to worry about which one's bigger, B or C or C or B. I even remember plugging it into Excel once, equals STDEV left parentheses, right? And realizing that the actual difference between B and C in terms of standard deviation is really small, and there'd be no way to easily approximate it. You don't have to. This is the GMAT. And so answer choice E is the only one that can work, and you have your answer. Now, it looks like lots of you found that or saw that in the answer choices. If you didn't, make a little note to look out below. Use those. As soon as you know something, you can look down on the answer choices and eliminate things that don't follow that rule. Now, let's talk about another conceptual way the GMAT can play with standard deviation. In this case, we added a number, and basically an extra number, into the bucket. But sometimes the GMAT will have you change the bucket, where you're going to alter all of the numbers in a set. For example, just visualize this for a second. If you were to take a bucket of numbers and multiply all those numbers in the bucket by a value greater than 1, what would that do to standard deviation? Make it bigger, smaller? Would it stay the same? Yes, Gerald, kudos to you. This would make it bigger. Just think about this for a second. If you've got 1, 2, and 3 in your bucket, obviously we've got average is 2, average separation is 0, 1, and 1. It's going to be a pretty small standard deviation. You multiply it by 10, you get 10, 20, 30. Now we have a 0, 10, and 10. Much bigger separation and therefore a larger standard deviation. Basically, this is what I like to call the map strategy for standard deviation. Multiplying a set by a value greater than 1 is kind of like magnifying a map. The points get farther and farther away from each other because the scale increases. You can see that the opposite would be true if we're dividing a set by a value greater than 1. 10, 20, 30, going down to 1, 2, 3, well, that's like taking a big map and then shrinking it down again. the scale decreases, and therefore the separation decreases as well. What about this though? What if you were to take a bucket of numbers and multiply them all by -1, in effect changing the signs of the set? What would that do to standard deviation? Bigger, smaller, stay the same? Gerald, you're on a roll there, and Elda as well. Hugo, got it. This would not change standard deviation. This changing signs is basically like mirror imaging the map. It might look really weird, but it's still the same distances. Notice whether you were driving from New York to LA or you're driving from LA to New York, the distance doesn't change. Incidentally, people look at this and go, that is really strange looking. But that is what the United States looks like from Australia, in case you were wondering. We call the Australia the land down under, but what if they're actually right side up and everybody else is upside down, right? Anyway, little geographical joke there. That was terrible, so I'm going to move quickly on. Now, think about this. What if you were to now take a bucket of numbers and you were to add a constant? Not throw a constant into the bucket to add to the set, but to add a value to each value in the set. What would that do to standard deviation? Bigger, smaller, stay the same? Say we added a 10 to each of the numbers. Yes, Gerald, Elden, Juan. Now, actually, Juan, it would make it smaller. If it's the same value added to everything, it would make it stay the same. Just think about this for a second. If we went 1, 2, and 3, and let's say we added 10 to each of these values, then it would be 11, 12, and 13. But since the average will naturally change, but the average separation between the numbers won't change. Adding and subtracting a constant to each number is basically like shifting the map. We still have the relative separation from things. We're just looking at a different starting point. Still the same separation. Make sense? Okay, let's do, so I just want to get one last problem in before we go to our first break. This is going to be a classic data sufficiency question that tests you on your ability to understand on a conceptual level standard deviation. Because it's a data sufficiency question, these problems tend to go a little bit quicker. My guess is you could figure this out in about a minute. We'll see you then. Okay, I can see we're still waiting on several to get in answers. Would anyone like a little bit more time? Okay, let's go ahead and talk then. This one's going to be fun. Jeff, you want to close the polling station? You can see we're mostly split between either C or E. In other words, combined or they don't work. They don't work at all. And really, good job on this one for eliminating A, D, and B. You should be able to do this fairly quickly. Think about this for a second. I'm going to use the official Greek term for standard deviation, sigma. Okay. So we're trying to test, is the standard deviation of set A greater than the standard deviation of set B? In other words, we kind of need to know at least some kind of numbers for both of them if we're going to get a comparable at all. And so notice, statement number 1, just saying something about set A doesn't tell us anything about set B. And statement number 2, telling us something about set B doesn't tell us anything about set A. Knowing individual pieces allows us to be able to eliminate A and B by themselves, and we get rid of all three. We are down to as either C or E very quickly. Now, this is a yes-no question. You see it? Is the standard deviation of A greater than the standard deviation of B? So basically, we're dealing with kind of a yes-no idea. Now, if we both have to be true simultaneously, it should be very easy to figure out that yes is an option. I mean, think about this. Consecutive multiples of 10. All right, 10 and 20 are consecutive multiples of 10. Consecutive multiples of 2. All right, 2 and 4 are consecutive multiples of 2. The separation between these numbers is naturally greater than the separation between these numbers, and so the standard deviation of A clearly can be greater than the standard deviation of B. So yes is an option. But remember, we've got to play both sides. While we showed that yes could be true, does it have to be? Can you come up with an exception to the rule that would give us a different answer to the question? And we're going to give kudos to the first person that can tell, actually maybe to everybody. If you can type it in, I think it's worthy of it. Yes, Elda, great insight there. Just to start us off, it never says the same number of terms. And so if we had statement number 2, if we had 2, 4, 6, 8, 10, 12, blah, 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 all the way up, heck, wow, that was supposed to be an infinity symbol. I'm not sure what happened. Well, okay, the smartboard is not letting me do that well. Okay, if we go up to infinity, well, an infinite range will create an infinite separation, okay? So it's very easy to have a larger standard deviation for set B. And as a result of that, we have a no is a possibility. Therefore, combined doesn't work. We're now going the other direction of the data sufficiency arrow. Combined doesn't work, and we have only one possible answer. And the answer is E. That was it. Great job for those of you that found that. A lot of people will fail to recognize that their brain automatically assumes the same size of the sets, even when it doesn't say it. And so if that's why you missed the question, just make a little note of it so that you're not making that assumption later on. And congratulations, you didn't make that mistake on the GMAT. Now let's step kind of back and talk tactically about what we just learned. First, do you notice that average or mean can be used to calculate unusual sums where you find the average then multiply the number of terms? Okay, there's major strategy here. With median, you need to arrange the number of terms in ascending order. Remember the game, set, match rule, that they don't have to be in ascending order. Also, remember with median that an evenly spaced set, the median equals the mean. And so sometimes it's easier to go from the median into the average without needing all the pieces. But you do need to have it be evenly spaced. The primary trap with mode is sets can be multimodal because there's the same number of multiple numbers of the same number of terms in a set. With range, obviously, there's no such thing as a negative range. And it can only be 0 if we've basically got a bucket of 5s, if all the numbers in the set are the same. And with standard deviation, probably one of the major takeaways here is the number of terms is important. Now, the other major takeaway with standard deviation is what I like to call don't deviate. You will never have to calculate standard deviation on the GMAT, but you will need to understand on what happens to it when you start changing around values. Okay, that's statistics. So let's take that first break, get up, stretch it out. We'll see you in 5, and when we come back, we're going to talk about combinations. I'm excited. We'll see you in 5. All right, ready to go to Vegas? Let's do this. It's time to talk combinatorics. Now, I mentioned that combinatorics is considered difficult by many test takers, but simply because they've never studied it before. But as you see, the GMAT combinatorics really is about the critical thinking skills. You knew that was coming, right? And we will cover the basic formulas and rules, but you got to make sure you understand the thought process to reason through these problems. So we really are going to go pretty deep in this lesson, even deeper than the manual goes, to help you understand the whys of the formulas, why they work the way that they do. Now, combinatorics, again, while some people consider it hard, they've actually shown the distribution of combinatorics questions is relatively consistent. Now, this is only over a very large sample of tests, so your individual tests might see some variations. But you see very easy combinatorics questions showing up on this exam. You see very hard questions showing up on the exam. And in a regular test, you will likely see approximately 2 to 3 combinatorics questions, regardless of your performance. I've had some students tell me that their very first question, as in question number 1, straight out of the gate, was a fairly easy combinatorics question that they were able to reason their way through. I've also seen combinatorics questions show up at the very end of a quantitative section of a very high-performing student too. Now, we need to begin with something that's not even in the manuals, but this really is going to create the foundation for combinatorics. Combinatorics is basically the branch of mathematics that calculates the different ways you can arrange things. The good example would be flipping a coin, heads or tails. Well, you could create a linear schedule of what you got, heads, tails, 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 heads, heads, tails, heads, tails, etc. And that's going to be a way to arrange things. Now, with flipping a coin, you should be able to notice that the system basically resets each time. Each time you pick something, as soon as you get a head, you could technically get 50 consecutive heads. Now, the odds of that are tiny, but still possible. But even though you've got 50 consecutive heads, the chances of you getting a heads the 51st time is still 1 in 2. The previous heads don't affect the present opportunity to flip a coin. This is what this creates, we call an exponential situation, where it resets each time you pick something. Now, I'm going to use a little bit of a different metaphor here that might resonate with many of you. Do you have any Scrabble players out there? I mean, I guess I have to say, do we have any Words with Friends players out there? Is that, I've never played Words with Friends. Is that like the I don't know, the cell phone app version of Scrabble? I wonder if Scrabble owns Words with Friends. If not, they probably should. So Michelle, it is. Okay. I'm an old school Scrabble player. I love to play Scrabble with my wonderful wife. Oh, okay. Oh, Michelle. The different name. That's enough to be able to say that they don't. There might be is there a lawsuit coming down the pipeline for that? Because I've seen my students play Words with Friends, and it looks pretty darn the same. Travis, Bananagrams, sure. Bananagrams, I've seen that game as well. Kind of the same idea. Basically, with Scrabble, in the old school version, you've got a bunch of word tiles in a bag. Obviously, in the app version, it's a digital version, but still, it's the same idea. You're pulling letters out of a bag, and your job is to arrange those letters to be able to spell words. Well, with an exponential, this would be equivalent to pulling a letter out of the bag and then recording it and then putting it back in the bag. Because remember, exponentials have to reset each time you do something. Maybe the first time you pick a tile out of the bag, you'll get A. Okay? There was 4 options you could pick from. A is the first one. Maybe the second time you pick a B, still 4 options because the system resets each time. Maybe the third time you pick another B, which is possible with an exponential because the B you picked in the second choice is still there. And then maybe the last time you pick an A that you already picked. And so whether you're the fan of a certain famous Swedish rock band, or you happen to know the Hebrew name for father, but they're both Abba there, it's that you can create this with an exponential. Now, let me visualize this in a little bit different way. Let's say you pick, you've got 4 options the first time around. And then after you've picked the once, well, then you pick again. And there's going to be an extra 4 options. So you've got 16 or 4 times 4 possibilities. A, B, A, C, A, D, B, A, B, 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 C, B, D, etc. The third time, you've got another 4 options. And the fourth time, trust me on this one, please do not adjust the resolution on your monitor. In fact, I can barely read it, and I'm standing here 2 inches away from it. But trust me, I actually did type these in. The 4th level also works. So you've got 4 options for each of the 4 options for each of the 4 for each of the 4. The pool of available choices, if you're picking 4 things 4 times, is going to be 4 times 4 times 4 times 4. Or basically 4 to the 4th power. Now, notice we just derived why the equation for an exponential works. If you're only picking 3 times, it would be 4 to the 3rd. So here's our equation. A is the number of arrangements, N is the number of options that you can choose from, and K, I don't know why mathematicians chose K in this equation, so I'm going to invent a reason. Is that okay? K is how many spaces you have in your final arrangement. In other words, your keepers, the number of individual slots that you are keeping in your final arrangement. There's your equation. Make sense? Let me give you an idea about what happens with exponentials, like an n to the k relationship. This is an n to the k relationship. Suppose you could fold a piece of paper in half 50 times. Now, in other words, you take a piece of paper, fold it in half twice, fold it in half 4 times. I want you to just imagine for a second how tall the stack would be. Here we have a young lady that took a fairly large piece of paper, folded it in half 11 times. There's your example. Here's 11. Sam's saying, does that get you to the moon? Good question, Sam. It actually goes further than that. And Sam, kudos to you for the way you're visualizing this. It would actually be a stack 70 million miles tall. That's about 3/4 of the distance from the sun to the earth, all the way in. That's a big stack of paper. And the reason why I bring this up is because I just need to have you understand that exponentials get really big really fast. They're a little bit of a form of orthogonalness, but on the other hand, you can use this concept to your advantage. If you realize you're dealing with an exponential question and therefore it's likely going to get big pretty quickly, if you look down to the answer choices and there's only one of them that gets big, well, you've got your answer in 10 seconds. Make sense? Incidentally, you want to know how big this paper stacking exercise can get you? If you were to somehow manage to take a piece of paper and fold that piece of paper in half, just boom, 103 times, that piece of paper would, a stack of paper resulting in that like folded piece, would cross the known universe. It would be over 93 billion light years across. That's a lot of paper. Anyway, I just did get the big takeaway, exponents get big really fast. Well, I'll show you some examples later on where we see this in action. Now you've got the basic idea behind an exponential. Let's talk about permutations. I had fun with this one. Here's Exhibit A permutation. And if you got that one, you're well on your way to enjoying the next stage. A permutation is different from an exponential in that it cycles down. So once you picked an element, it's gone. It can't be picked again. Now, permutations are also sequential. They form a linear or an ordered arrangement. But there can be lots of ways we see permutations. They might be a timeline. In other words, a schedule of events occurring. That's a linear arrangement. I've seen things like, I don't know, like vases on a mantelpiece, or like how can we order first, second, third places in a race, that sort of thing. First, second, third place, that's a linear ordered arrangement. Now, Can we play a little bit of Scrabble here again so you can kind of visualize this? So here we have our 4 Scrabble tiles. Our first choice, well, we still have 4 options. But now, let's say we picked B out of the bag. Now, because it cycles down, B is not an option anymore. And so our second choice, we only have 3 possible options from which to pick. So now let's say we pick D. Now that option is gone. It's cycling down. It's a countdown, basically. The third choice, let's say we pick A. Well, now that one's gone. And technically, our last choice we've already chosen with our second to last because there is only one left. And let's say we pick C. 4 times 3 times 2 times 1. Now, visualizing this in the same way we did the exponentials should get you a feel for how permutations are a lot smaller than exponentials. We've got 4, and then 3, and then 2, and then 1. Now, if you can't tell the difference between this diagram and our exponentials diagram, maybe you do need to adjust the resolution on your set or potentially get a much better prescription for your eyewear. The permutations are going to be a lot smaller. And now 4 times 3 times 2 times 1 can be condensed down, and we have a permutation. Now this is a number multiplied by all previous positive integers. So 4 factorial is 4 times 3 times 2 times 1. It's signified by an exclamation mark after an integer. This is not the GMAT getting excited. The answer is 4. Okay? No, GMAT doesn't get excited. This is business, right? Now, factorials, for obvious reasons, can only be positive. There's no such thing as a negative factorial. And factorials can also be factored. But I'm going to give a little bit of a metaphor that might help you remember how you factor factorials. Have anyone seen the original Shrek movie? This is almost becoming an old movie. I'm trying to remember when the original Shrek came out. Good. Like Sydney's seen it. Sydney, we're going to give kudos just for being cultured like that. It's yes, like ogres have layers, and so do onions. Think about the concept of peeling an onion, though. Okay, if you peel the outer layer of an onion off, wow, really? It's been 18 years. Michelle, we'll give you kudos for that anyway, but we almost need to have negative kudos because you just made me feel old. No, I'm kidding. Yeah, so it has been out for quite some time now. But basically, you peel an onion off, and you have a smaller onion. Make sense? You peel another layer off out of the onion, and you still have a smaller onion. You can keep peeling layers off of onions, and while it might lead to a rather tearful experience, you can peel off a layer, and you just get smaller and smaller onions. However, if you want to get to the middle of the onion, it's going to destroy the onion. Well, in like manner, factorials can be peeled. But they can only be peeled there. They can peel your outer layers off, and you'll still have a smaller onion. In other words, 7 factorial is 7 times 6 times 5 factorial. But if you want to somehow factor a 2 out of this, you're going to either have to take it from the 6 or just get rid of the factorial altogether. Now, this peeling of factorials idea will come in very handy as we start getting into some problems. So just pay attention to this basic rule of peeling onions. Now, there are technically an infinite number of factorials because factorials are just based off of integers. So don't memorize them all, but definitely memorize them up through about 7 factorial. Now, this doesn't mean that you'll only be dealing with factorials in this range. But I've noticed that the pattern of the GMAT is anything above 7 factorial, it tends to keep in factorial form. They're not going to multiply out 22 factorial and have that as an answer choice. They just don't. That's a version of orthogonous. So they'll keep 22 factorial in factorial form. But when you get down to this range, they tend to shift it just into integer form. Now, I want to draw your attention to one thing, 0 factorial. 0 factorial is mathematically defined as 1. And it's basically neener, neener, ha ha, you can't change that. It was defined by mathematicians to be equal to 1. Now, we're going to give you some equations in a little bit that will explain why 0 factorial must be equal to 1. But really, the rules of factorials don't apply to 0 factorial, but you have to make this work in order for the equations to function. You'll see in just a little bit. Now, let's visualize permutations in a little bit different way. Instead of picking 4 times, let's just pick twice. Notice, we picked twice. Well, we still have 4 options the first time, and then we've got 3 options the second time, and then we're done. So if we were to go from 4 times 3 times 2 times 1, so it's just 4 times 3, we're basically eliminating these bottom 2 layers and therefore eliminating the smaller onion, I guess you could say. Now, mathematically speaking, the way you eliminate a smaller onion is you divide by the onion. Does that make sense? You want to get rid of 2 times 1, you divide by 2 times 1, and it will divide and conquer, and you'll just be left with 4 times 3. Well, guess what? We just derived the equation for a permutation. Here it is. The number of arrangements is n factorial, but we're dividing by n minus k factorial. Now the n still stands for the same thing. It's the number of options you can pick from. K still stands for the same thing. These are the spaces in your final arrangement, your keepers. And notice what happens. If you're keeping all of them, then n minus k would be 0. And 0 factorial, do you see why 0 factorial must be equal to 1? Because otherwise this equation explodes when you're picking all the items. Because 0 factorial, like n factorial divided by 0 is, we basically just exploded the math at the speed of light. Sydney, good question. Sydney asked, how does this equation change if you're picking more than one thing at once? Good, Sydney. I have seen those situations on the GMAT, and the answer is zip. Now, there are some variations when you're picking subgroups. But if let's just say you reach your hand into a bag and pull out a bunch of numbers and put them on the ground, because you still have to arrange them linearly, then the equation is then it's the same. Now, Sydney, there's also another type of problem we're going to talk about later called a combination. Now, a combination is when the order doesn't matter. So you're picking a whole bunch of stuff out of a bag and just saying, I want this, where there's not a linear arrangement of things, then you will see a different equation. And I'll give you that equation in a little bit. So I'm not sure which aspect of that answer you were thinking of, but if it's still a linear arrangement, then okay, good. So if it's still a linear arrangement, then it's still, you're just talking about the number of ways of doing it, and this equation will still hold for that. Good question, Sydney. Yeah, some people, I've actually seen some problems where the test deliberately inserts the word simultaneous into the scenario, like thinking that's going to throw people off. It still doesn't change the mathematics. As long as you're having to linearly arrange the elements. And that's the critical distinction. That's what makes permutations function. Good question. Kudos to you. Let's do a problem together. And I want to see if you can kind of figure this one out. Man, I look at this problem every time and I think, I wonder if we're going to have to update this. I'm just thinking about DVDs from a video store. It's like, you want to talk about ancient history, there it is. I actually read an article. I guess there's only one Blockbuster video left on the planet. I think it's in Oregon, if I'm remembering correctly. But I think we could still say, everyone's like, what's a DVD? It's what was in Alaska? I thought the second one was in Alaska, and they finally closed. I think we're down to one more. If I'm remembering the story correct, I think the Alaska was the second to the last, and now we're just. I think it's now just Oregon. I think that's all that's left. I think I'd say you'd have to. I'm sure someone out there could probably do that research quickly. So in the end, we could pretend that this is, I don't know, videos in your Netflix queue. Yes, David, I've heard they're thriving. Like people are actually making it a vacation destination just to go to that Blockbuster store in Oregon. And I hear they're making more money off of the merchandise than they are off of actually renting videos. In any case, let's talk about Bill and his lack of social life. He's choosing 3 DVDs from a list of 8 new releases and then deciding in what order to watch them. Now, let's do this first with the equation. Okay? We have n factorial divided by n minus k quantity factorial. That's the number of arrangements. Now, you see we've got the linear arrangement. He's creating a schedule of videos. And he's obviously not watching all 3 videos on 3 different screens simultaneously, so we've got a timeline happening. This is a permutation. Now, you can also see the rules of the game. It says he cannot watch the same video more than once. That's also necessary. This means that it's cycling down and we have a permutation. Quick kudos. What would happen if Bill could just watch the same video and over and over and over again? Maybe he just really likes Avatar: The Last Airbender or something like that and just has to watch it 3 times. How would that change the problem? Or what problem type would it be? Actually, Travis, it's that you're thinking more of a combination. If you can watch the same thing over and over and over again, there still is an order. Make sense? You're still watching movie, but yes, this is where it would be an exponential, and you just have an n to the k. So notice that like the devil's details, it's going to change the equations entirely, so you've got to read them carefully to realize, wait, are we dealing with an exponential? Wait, are we dealing with a permutation or a combination? Again, Elder will talk more about those in just a little bit. In this case, though, it is cycling down, and we have a linear arrangement, so we've got our equation. Now, what's n? Give me the number. Excellent. Wow, we got lots of you typing that in. Gerald, just barely with the fastest internet in the land, or fastest reflexes, the case may be. N is equal to 8. We've got 8 new releases. How about K? What's K? Awesome. Looks like Sam just barely squeaked ahead on that one. Great job. K is 3. We're choosing 3 DVDs. So now we've got our equation. It's going to be 8 factorial and then 8 minus 3 quantity factorial. Well, 8 minus 3 factorial is nothing more than 5 factorial. And now can you see how to peel the onion? We have 8 times 7 times 6 times 5 factorial divided by 5 factorial. You peel the onion out far enough so that you can divide and conquer. You get rid of the top and the bottom. We've got 8 times 7 times 6. And look down at the answer choices. Seriously, don't do this math. 56 times 6 is going to have a units digit of 6. It's going to be answer choice D. Now, I want to do this problem another way. And this connects in to a tactic I call Be Wise, Visualize. Many combinatorics questions are solvable without even using the equations at all, if you understand the basics of the game. For example, notice Bill is basically trying to set up a schedule of 3 videos that he's going to watch. Now he's got 8 possibilities, and so the first video that Bill can watch, there's 8 videos from which he could choose. And once he's chosen that first video, for every one of those first videos, those 8 videos, he's got 7 options he can choose for the second possibility. 56 options if he's choosing 2. And for every one of these 56 options, there will be 6 remaining videos from which he could pick to get that third option. 8 times 7 times 6. Now, that's this piece right here in this equation, but you notice on how you don't even need the equation in order to be able to figure this out? If you could just get, wait a minute, I know how permutations play the game, 8 times 7 times 6, we've got our answer. That's it. Feeling good? Let's add some additional complexity now. It's time to talk multiple Ks. Now remember, Ks are the number of keepers in our final group. And there's some solid leverage words that help you to know when we've got multiple keepers. Or is probably one of the biggest one. That's, in other words, 2 or 3. Now whenever you see or, then you've got to, this basically splits the problem into a couple of smaller combinatorics questions. You solve for each of the group size. If it's 3, great, solve for 3. 4, great, solve for 4. And then what you do is you add them together. Now, there's other types of multiple Ks, the at least or at most words as well. At least 3, well, that's going to be 3, 4, 5, up to the maximum number. At most 3, well, it's going to be 1, 2, and 3. It still use the exact same rule. It's basically a this or this or this. Then you solve for each group size from the minimum number to the maximum, and then you just add them together. Now, we called this GMAT Jiu-Jitsu issue either or addendums. Either this or this, you add them. Does it help you remember it? Either or addendums. Basically, or you add them. Now, I want you to try this one on for size. This is going to be an either or addendum. It's now time to go to the worst job in the history of the planet. Mike is a DJ at a high school radio station. Clearly, Mike did not do very well on his GMAT. So I want to see what you can do. Go ahead and read it, and then we'll give you about 90 seconds to solve for this. We'll see you in 90. Beautiful job getting those answers in. Let's come back and talk. First, I'm going to avoid the equations here. Can you see why? We just need to be wise, visualize with this. It says 2 or 3 more songs. There is your leverage indicating we've got an either or addendum. So we've got a 2-song option and we've got a 3-song option, and we're adding those 2 together. Now, we've got a list of 10 songs. You'll notice it says the songs cannot be repeated. Even a DJ at a high school radio station knows you just can't play the same song over and over and over again. It's like, seriously, you get fired even from that job. So notice, since the songs can't be repeated, we've got a permutation, cycling down. If you're just playing 2 songs left over at the end of the prom, you've got 10 songs fitting in the first option, 9 songs fitting in the second option, 10 times 9. And then you've got 10 times 9 times 8 if you've got 3 songs that you could play. Well, at this stage, notice this is 720 plus 90. But seriously, don't even do that math. Look at the answer choices. Answer choice B is just the 2 songs. That's a trap. Answer choice D is just the 3 songs. That's a trap. It's got to be bigger than D, and there really is only one answer. It turns out to be answer choice E. Now, fantastic job. Looks like the majority of the class got that one right. The key leverage here for this either or addendum is that phrase 2 or 3. That's it. Let's try another one. Now, I'm going to give you about 30 seconds more on this, in part because there's another layer of issues, but I've taught you how to think about this question. I want to see if you can spot, first of all, what question type it is. That's really the key here, to make sure you're focusing in the right direction. And then it's time to use your GMAT Jiu-Jitsu critical thinking skills here to turn out to get the right answer. Let's see what you can do. Ready? Play the game. All right, looks like we might even needed that extra time for this particular question, but that's okay. It looks like we got the supermajority of people putting in those answer choices. So let's have our little tactical talk. You can see the majority of the people that have put in answers have picked answer choice D. But in order to be able to get here in a meaningful amount of time, you have to use some GMAT Jiu-Jitsu. But before we start, I want to see who can tell us what combinatorics problem type are we actually dealing with here? Did anyone spot it? Excellent, Gerald. Yes, this is an exponential question. You can see the phrase, all the letters can be repeated in any one code. In other words, because of that repetition, it's no longer cycling down, and we don't have a permutation issue. Now remember, exponentials get big really fast. Well, look at the answer choices. The answer choices would be another good clue that you might be dealing with an exponential question. These are enormous numbers. So watch this. We've also have some additional leverage. It says the phrase, at most 3 letters. That means we're dealing with an either or addendum, so we've got to add them up together. But that means K is either 1, 2, or 3. And so with an exponential, this is going to be 26 letters to the first power, n to the K, plus 26 letters to the second power, plus 26 letters to the third power. And that is our actual answer. Now, that is also muthugliness. Okay, that's a lot of work. So, who got to the answer quickly that could help us see it? David, thank you. And I like how you're thinking there. David asked, hey, could we just remove B and C because they're so similar? Now, David, to be honest, that's not necessarily the case. Similar answers can sometimes mean one of them is right and the other is almost right. Does it make sense? So we can't quite play that game. However, Juan and Megan, you've got some great suggestions there. Yep, that big unit idea, the units digit concept. 6 times 6 is 36. So multiplying a big number with a 6 at the end isn't going to change the units digit. So in this case, 26 is going to be blah, 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 6. 26 is going to be a slightly smaller blah, 6. And then, of course, 26 is just 26 options. So we've got 3 different numbers, each with a units digit of 6 added together. And in the end, answer choice D is the only one that gets us there. So way to think like a test maker there. So we've got some GMAT Jiu-Jitsu masters. Travis, and kudos to you for seeing that too. So it's I knew one of these was. I wasn't sure which one, but because I hadn't worked it out yet. But C is the right answer to the wrong question. C is just 26 to the 3rd power. So in the end, D is it. That's it. Great job. That was not an easy question, and to be honest, we knocked that one out of the park. Actually, Travis, seriously, congratulations. You didn't make that mistake on the GMAT. Now you can step back. Remember the feedback loops pattern. You go, all right, why did I miss it? My guess is, Travis, you might have been moving a little bit too fast as you were reading it, and the leverage that you definitely missed was the at most. This is what gets you realizing we've got an either or addendum. So now that you made the confession and noted it, you're never going to make that mistake again, and now you're one better. All right. Now, let me give you a little bit of a hypothetical here. You don't need to calculate this, but it's now time to add another level of complication. These are permutations with repeats. Now, a permutation with repeat is different than an exponential. An exponential, you can repeat things as elements as many times as you want to. The entire situation resets each time. But sometimes you can have repeated elements. Instead of A, B, C, D, what about A, B, C, C? Well, notice what happens with our visualization of our Scrabble tiles. So anytime there is a D, we're now going to make that a C. And at this stage, notice we have a bunch of combinations that are the same. And so if we're looking for unique combinations, we permutations with repeats eliminates a whole bunch of options that are already there in other parts of our diagram. Now, we could spend quite a bit of time talking about how this equation gets there, but to be honest, I'm just going to give you this equation. Here is the equation for a permutation with repeated elements. And R is the number of times each element in the set shows up. Now, this can technically show up as many times as you want to. And you'll also notice that since we're not talking about the extra times, but just number of times an element shows up, if an element shows up once, then we have a little implicit 1 factorial here in the bottom of the fraction. And 1 factorial is just 1. So even in the regular permutations formula, we technically have a bunch of R factorials. We're just assuming that all of the elements are different. Let's do an example here. It's time to go 1 Mississippi. Now, I want you to imagine for a second the GMAT's going to ask you how many different ways can we arrange the letters of Mississippi if we don't have to spell an actual word. Now, let's also assume that we're going to have to use all of the letters here. It makes sense. Otherwise, this problem is no longer on the GMAT. If it could be 1 or more possibilities, then we're going from 1 to 11. But you can see we do have 11 options. And so n is going to be 11. 11 factorial is at the top. But now we have to divide it by a bunch of r factorials. And I'm going to deliberately do this. Okay? M shows up once. Now I realize 1 factorial is just 1, but just to help you remember that each factorial, even if it's 1, is still showing up in the bottom, helps to see what's happening. We have 4 i's, so we're dividing by another 4 factorial. We have 4 s's, dividing by another 4 factorial. You see how we're getting this number smaller and smaller and smaller? And then we have a couple of p's. 2 p's, we've got a 2 factorial. And there we are. To be honest, I think that 1 factorial would drop out of the answer choices. There's no reason to necessarily have that there. But if this were an actual GMAT problem, this is basically what you're looking at. Generally speaking, the GMAT wouldn't simplify this down any further, in part because of that 11 factorial. This is just, remember, factorials above a factorial just get ugly, and so they tend to stay in factorial form once you start hitting numbers of that size. Make sense? Let's go ahead and go to our second break. Now we still have some combinatorics issues we're going to cover when we come back from the break. So yeah, don't immediately shift gears into probability quite yet. We still have some great complicating factors once we come back from the break. But I want you to be fresh for these. So we'll see you in 5 minutes. Go get the blood sugar up or go get your heart rate up, whatever you need to do. We'll see you in 5. Time for our grand finale. Let's keep going. Remember how I promised when we come back from the break, we're going to add kind of some extra complications to combinatorics. And this is where you start seeing upper level combinatorics questions showing up. We're going to begin with the concept of combinatorics with extra rules. You might have seen some problems like this on some practice tests. This is where they give like ways where it doesn't work. How many ways can we arrange blank if something can't happen? For example, how many ways can we, I don't know, arrange people around a table, but Bill and Sue can't sit next to each other? Well, there we have the if Bill and Sue can't sit next to each other, here is this what we call a constraint. Now, when you see a constraint, you basically need to do one of two things. Remember, first of all, you're training your mental reflexes to go, when I see blank, then I do blank. When you encounter exception, there's two approaches. First, pretend that the rules don't apply. In other words, Bill and Sue can totally sit next to each other, no problem. Now that tends to be a much easier question, so you can solve that rather rapidly. And then what you do is then you think, all right, well, how many ways could Bill and Sue sit next to each other? And then what you do is you calculate or calculate those number of cases and then subtract that from the problem without constraints. Now, because this is the GMAT, often the no constraints answer is one of the answer choices. This is one of those trap answers. And so you can eliminate it, and then sometimes you can even just estimate the impact of those restrictions without needing to do all the calculations. So this is one of them. The other way is, and this is especially useful if the constraints are very limiting, then you only figure out the scenarios that work. Just come up with, all right, this will work, this will work, this will work, that'll work, and then add up the number of possibilities for each of these scenarios. Now, depending on the problem, it's either of these ways of approaching a constraints question will be faster. And there's no easy rule that will help you to know which one's which. I will tell you, generally speaking, that if you've got constraints that are very limiting, it's easier to think about how it works, the second option. If the constraints are only slightly limiting, then doing it this way is probably the faster. But there's no easy way to tell the difference between slightly limiting and very limiting. You just got to kind of do this by experience. Let me show you an example of a question that does this exact thing. And I'm going to solve this problem both ways, just so you can see the approaches. So this says, John and 4 friends go to a Lakers game. In how many ways can they be seated in 5 consecutive seats? Now, that would just be a standard permutation question, a linear seating arrangement. But here's where the constraint comes in. It says if John has to sit between any two of his friends. Apparently, John is xenophobic. And so he can't sit on the ends, is another way to put that. Well, let's first of all do the pretend John is fine with strangers situation. If John is fine with strangers, then the situation is really easy. We've got John and 4 friends, which means 5 people. And if it doesn't matter, then we've got 5 times 4 times 3 times 2 times 1, or 120 options. Now, that's not the right answer, but it gets us closer because we have to subtract the ways that it doesn't work. So obviously 120 is it. Now A is even bigger than the maximum, so that's clearly not right. We've already got it down to a 1 of 3 answer choice. But now we need to go, all right, which ways don't work? And it doesn't work if John is sitting at the end. Now we still have basically 5 seats. We want to visualize this. John sitting here, can't change that if we're looking for ways that it doesn't work. And so notice, 4 friends. If John sits there, we can still arrange his friends 4 times 3 times 2 times 1 ways. And this is 4 factorial, or 24. Now, you subtract 24 from 120 and you get 96. But that's not the right answer. Who can tell me why? Nailed it. Absolutely. There's more than one end where he could sit. So if we have boom, 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 if John's sitting here, Then we have 4, 3, 2, and 1 scenarios there. 4 times 3 times 2 times 1. And notice we've got another 24. Now, Travis, I like how you're thinking there. Travis said, what if the row is only 5 seats? In this case, this isn't just he can't sit next to a stranger, is he must be surrounded by 2 of his friends. Do you see that, Travis? So my way to just visualize this, where like he can't sit next to strangers, is just a quick way to say it. But this is, he has to be between his friends. And so it doesn't really matter if the row's only 5 seats. It still wouldn't work if John is sitting on the ends. But I like how you're thinking there. That would be, now that wouldn't be a calculable problem because we don't know if that is even a possibility. So we can't play that game. Does it make sense? But the GMAT keeps that from happening. But I like your thought process. You're anticipating potential threats. So in the end, 120 possible ways. Subtracting 24 gets us to C, which is the trap answer. Just counting the exceptions gives us E, which is another trap answer. Oh, the GMAT's good at what it does, isn't it? And we've only got one answer choice left over. It is 72. That's the right answer. Now, I'm going to do this problem again. This is the pretend there's no problems, then subtract the exceptions. Okay? Now let's just look at just the ways that it works. Well, if we've got 5 spaces, if John sat in this seat, it would work. And we can arrange his friends 4, 3, 2, 1 around him. There's 24 different ways. Now, John could also sit in the middle seat. That would work. We can arrange his friends 4, 3, 2, 1 around him. And John could sit in the 4th seat. That would also work. And arrange his friends 4, 3, 2, 1 around him. And so there's 24 ways for each of the places where John could legally sit, at least follow the rules of the problem. And 24 plus 24 plus 24 still equals 72. And we've got our answer. Notice this problem, either way you do it, it's going to be 3 combinatorics questions. Just kind of see what's going on. So there's not necessarily one advantage over the other here, but in both cases it gives us the right answer. Okay, those are combinatorics with exceptions. Now, last but not least, it's time to talk combinations. Now, please don't get confused with this term. The word combinatorics refers to all different ways of calculating arrangements of things. So we see the word combinatorics doesn't necessarily mean the same thing as combinations. The word combination has a very technical meaning in combinatorics. These cycle down just like permutations do, but a combination, the end result is unstructured. Now, remember the question we had a little bit earlier about what if we just picked a whole bunch of stuff all at the same time, kind of a simultaneous choosing? And we said, well, that still doesn't change a permutation. It also doesn't change a combination if we do it one at a time. It's still possible to pick elements one after the other, after the other, after the other. But if in the end order is irrelevant, then we still have an unstructured result. It's not about how you pick them, it's how you order them in the end that changes it. Now, with a combination, since order doesn't matter, just a pile of stuff, then we really only have, if we're picking 3 keepers out of 4 possible options, we only have 4 options. Because ABC is going to be the exact same as CAB, which is the same as ACB, which is the same as BAC, etc. These are no longer different ways of arranging if order is irrelevant. Now, if this helps you to remember what a combination is, I'm going to compare a combination to a combo meal. Now, I don't know who here has last had a combo meal, Basically, if you order a combo meal, it's whether you get a burger, drink, and fries, or a drink, burger, and fries, or a fries, burger, and a drink, or hey, you go to Wendy's, you get a chicken sandwich and a side salad and a Frosty or something like that. Whatever order you order it in, wow, Gerald, looks like you win the competition there. Nice. Okay. So basically, Gerald, this is going to resonate with you, I think, on a very personal level. Whatever order you order your combo meal in, you can choose to eat it in whatever order you want to. Basically, it's just unceremoniously given to you on a platter. You go here, boom, done. Okay. Now, combinations are combo meals. In other words, the order doesn't matter. However, permutations, this is like you need to get your hair done in order to be able to go to it. This is like a multi-course meal. It's a permutations, the order really matters. You have your hors d'oeuvre first, and then your palate cleanser, and then you might have your soup, and then you might have your salad or whatever. And so the order of a permutation requires a perm. The order of a combination is a combo meal. Does that help you to be able to remember the difference between the two? Now, here's the equation for a combination. K is still there. It's still the number of spaces you have in your final arrangements. In other words, your keepers. And you should notice that the relationship between the permutations formula and the combinations formula is really close. The only difference is this extra K factorial here in the bottom of a combinations. And you can use this to your advantage. Do you remember how we showed you the Be Wise Visualize technique for permutations, where you don't actually need to plug stuff into the equation to be able to figure things out? You just basically go, all right, here are the number of options. Well, obviously with a combination, you don't have this linear arrangement. However, you can still do it. And let me explain why. Naturally, there's going to be more permutations than combinations. We're dividing by K factorial, and order is irrelevant anyway. And so you might be able to leverage answer choices against each other. But it's also not necessary to remember. If you don't care about the arrangements, notice what you can do. You could pretend, look at this, you can pretend that you're dealing with a permutation and therefore use the Be Wise Visualize quick strategy. But you just have to remember at the end, you've got to divide by K factorial. Maybe do something as part of your target. So you're realizing, all right, don't forget, while we're going for the number of arrangements, we've got to make sure we're dividing by K factorial. Just do something like that so that when you're solving for it, you're not accidentally solving for the wrong problem. You're almost guaranteed that to be the case. Now, the next level is what we call simultaneous scenarios. When we've got, bumped up against it, there we are. When you've got scenarios where there's multiple possible ends. In other words, we have subgroups happening here. Then what you do is, where you have to have this group and this group, you multiply the number of arrangements for each individual subgroup together. Remember, or, it's an either or addendum. Either this or this, you add them. But if it's this and this, a simultaneous scenario, you multiply them together. Let me show you an example of this. It's time to go to a high school track tryout. You've got 8 women, 5 men competing for 3 male and 3 female spots on the decathlon team. Now think about the concept of a team. There's no order here. This is not first, second, third place or captain, vice captain, water boy or whatever. We just have people on a team. So this is a combination. This is a combo meal. Just like, I don't know, like photos in an envelope. The order is irrelevant. It doesn't matter. Maybe we've got like marbles in a drawer. Yet order doesn't matter here. Any of those scenarios, we're dealing with a combination. Now remember though, with a combination we can pretend it's a permutation so long as we're dividing by the K factorial in the end. So watch this. Let's just look at the 8 women spots. 8 women, 3 spots. If the order mattered, that would be 8 times 7 times 6 options. Make sense? Now, because order doesn't matter, we've got to divide by K factorial. Now, divided by K factorial in this stage is 3 factorial. And 3 factorial is 6. So we could just go, oh, boom, got it. Divide and conquer. We've got 56 ways of arranging the women in those spots if order doesn't matter. Now, for the men's team, we still have 3 spots. 5 times 4 times 3 would be the value if order mattered. Now we've got to divide by k factorial. Still 3 factorial there, dividing by 6. This is going to turn out to be 60 divided by 6, which turns out to be 10. Now, here's where one of the big traps comes in. You add them. You pick answer choice D and you get it wrong. This is not an either this or this. It's not an either or addendum. You see that we're not picking either a women's team or a women's team to be able to represent. We're picking a women's team and a men's team. So for every one of these arrangements, we can arrange the men's team 10 different ways. So D is a trap answer. C is it. 560 different ways of arranging it. Feeling pretty good? Okay, we're ready to kind of finish off combinatorics. And so let's step back, look at the tactics. First, notice, you want to think conceptually and visualize these things. It would be a very rare problem indeed where I would do a combinatorics question in my head. Just the basic concept of visualizing, drawing out spaces just so I can see what's happening. This keeps you from just missing details here. And you can also avoid messy math by just visualizing what's happening, the be wise visualize idea. No, you also want to know how to leverage the formulas for permutations with repeating elements and combinations. Notice, so I didn't say use the formulas, I said leverage them. The be wise visualize works for all permutations. So if you can start here and then divide by r factorial, you've got the repeated elements. If you can start here and divide by k factorial, you've got the combinations. You also need to know how to deal with restrictions. Remember those 2 different ways of thinking about constraints. And then can you see how you need to read very carefully for details? Does the order matter? That changes it. Are repeats allowed? That changes it. You can see as well why you've got to read these very carefully because a small change in the scenario will create a large change in the math, and you're almost guaranteed to have that oops, that wrong question represented in the answer choices. You can also see why combinatorics is perfectly aligned to be in a critical thinking test like the GMAT. There's not just one equation you just plug and play with. You've got to be able to kind of create your own equations as you go, and you want to meticulously, carefully read in order to visualize and understand the scenario before you start on the problem. This is looking an awful lot like all sorts of critical thinking skills are at play here. You see it? Let's finish strong. We've got a little over a half an hour, and it is time to hit probability. Now, the basic concept of probability, I know you know. A probability is a number of outcomes where something occurs divided by a total number of possible outcomes. Basically, probability is A divided by A total. Now, a probability describes the likelihood of something happening, and it can range from 0 to 1. You can never have a negative probability, and you can never have a probability larger than 100%. This always happens. There's such thing as a 110% chance of something occurring. Now, I just want to make sure you've got the basics of probability down. So this is going to be a very rapid problem. 30 seconds should get you there. If everybody gets it right, we'll throw a little party and then move on to the next stage. If we do have some people missing, I want to slow down and make sure you understand the details here. So ready? This is where we really are going to Vegas. Time to roll the dice. See what I can do. Awesome job. Okay, looks like we do have some different answers that are being put in, so this one we might want to slow down and take a look at. Remember that a probability is a number of times where something occurs divided by the total number of times. Now, for a total number of times, this one's pretty easy to spot. We're rolling a fair six-sided die. Now, incidentally, I've never, in my 13-year career of getting people ready for the GMAT, I've never seen the GMAT talk about a loaded die. But for some reason, they like to include fair dice as part of the scenario. So we've got an amount. In other words, the number of times when it works divided by the total number of times. Now, with a six-sided die, that total is going to be pretty easy. This is going to be divided by 6. But now we need to go, well, how many ways does it work? Well, this stage, this is small enough. I'm just going to put it down up above. What's the probability the number is even? Well, even numbers are going to be 2 or 4 or 6. And it says even or less than 4. Now notice, not even and less than 4. If it's even and less than 4, in other words, it has to fit both of those criteria, then there's only one number that's even and less than 4. And the answer would be A. Looks like we had a couple people pick A. So if you did that, you read the problem too quickly. But even or less than 4 means either of those scenarios would work. And less than 4 would include 1, 2, or 3. We do have an overlap here, but in the end, this is one of the numbers we can roll, so it's not like it matters more than the others. You see it? And in the end, we have 1, 2, 3, 4, 5 options that fit even or less than 4, and so that A is just nothing more than a 5, and we've got 5, 6 is the right answer. Any questions? Let's go back to Venn diagrams to help us visualize the concept of probability. And I want to do this one kind of quick, just to refresh your memory here. I want you to imagine for a second that the yellow rectangle represents all of the possible situations that could happen. And then you've got A, this is the scenario that we might be worrying about. This is going to be a subset of the total options. Now, you also have what's called complementary events. These are events that are guaranteed to happen, but you're not sure which one. The probability of A or B occurring is 100%, but they can never simultaneously happen, so the probability of A and B occurring is 0. Flipping a coin would be a good example of a complementary event. It's either heads or it's tails, and it physically can't be both. Now, we also have what we call mutually exclusive events. These are events that can never be both. So the probability of A and B occurring is 0. But if you're just caring about the probability of something happening, then you add the percentages. Let's get a specific example. Let's say Michelle is applying to Harvard and Stanford. What do you say, Michelle? You game for it? Now, notice Michelle isn't going to get 2 MBA degrees. Okay? So we're going to have the probability of her getting a degree from both Harvard and Stanford. Well, that's 0. Okay? Nobody gets 2 MBAs for kicks and giggles. But let's say Michelle has a 20% chance of getting an MBA from Harvard, and let's say a 30% chance of getting an MBA from Stanford. 20 plus 30 would be a 50% chance of Michelle getting a degree from one of those 2 schools. We could add the percentages here. Now, we also have what we call co-occurring events. And Michelle, if I could use kind of as the example, obviously, if Michelle's going to either Harvard or Stanford, Michelle's going to apply to both schools. Now, this first one, the mutually exclusive event, is the chance of her getting a degree from one of those 2 schools. But there's also a probability that we're just talking about getting accepted to one of those 2 schools, that we're going to have some overlap. Maybe Michelle's application is so solid that both Harvard and Stanford want her. And this just goes right back to our Venn diagram scenario we talked about earlier. The probability of one or the other occurring is you add the two probabilities together, but if you've double counted the middle, then you have to subtract the probability of Michelle getting accepted to both Harvard and Stanford. Awesome, Michelle. By the way, good luck with the application process. It's a, man, 50% chance of going to one of those two schools. That's really good. Awesome. Now, let's talk about that probability of one and another event occurring. You already know the basics for this. One and something, you multiply it together. One or something, you add it. This either or addendum versus simultaneous situations. So if they're what we call independent events, in other words, Harvard doesn't talk with Stanford, Stanford doesn't talk with Harvard, you're just multiplying the events together. Now you also have what we call dependent events. Dependent events is where the probability of one thing affects the probability of the second thing occurring. This is what we call a conditional probability. The probability of B if A. Okay? Now notice you're still multiplying the probabilities together, but they're calculated slightly differently. Let's do a problem that shows the nuances of these ideas. So you can see the acceptance rate at a certain school. So David, looks like this is a question about you. How does this sound? So the acceptance rate at a certain business school is 15% for first-time applicants and 20% for all reapplicants. Okay. So David is applying to. Let's see, David, what's your top pick? Well, let's make this personal. Type it in. Awesome. David, Stern School of Business. Yeah, phenomenal program. All right. So this is David applying to NYU. Now, obviously, David's chances are higher than this, but we'll go ahead and use these percentages. Right, David? So 15% for the first time, 20% for a reapplicant. If David's applying to the Stern School of Business the first time and will attend if accepted, what's the probability that they will have to apply no more than twice? Now this phrase, no more than twice, is kind of interesting. Notice he's either applying once or he's applying twice. Now in either this or this, we're going to be adding the probabilities. However, there's a great trap answer here. And kudos to the first person that can identify the answer that is so obvious, it's obviously wrong. Absolutely, D. Like, seriously, this is the GMAT, people. We're not just going to go, oh, look, 15 plus 20, done, and call it good. This is the answer that can never be right. Remember the concept of mind games. GMAT's both hard and easy at the same time, but that means it must be hard. Awesome job. So let's look at this probability, though. The probability of him getting accepted the first time added to the probability of him getting accepted the second time is what our real target is. Now, first time is easy, 15%. That's there. There's no negotiating. So that is our 15% as an option. Now, you could also see that there's no way we can get above that. I mean, we could technically eliminate E as a possibility as well. But take a look at this second possibility. Now, if he's applying for the second time, it means that he must also have been rejected the first time. Otherwise, he would never apply the second time because it says he's going to apply, he's going to attend if he's accepted. Do you see it? And so it's kudos to the fastest reflexes here. What's the probability of David not getting accepted the first time? Absolutely. If 15% chance of him getting in, that means an 85% chance of him not getting in. Now, this is him not getting accepted, but now it's this and getting accepted. So this is going to be not getting accepted and getting accepted the second time around. Do you see the difference? Here we have an either this or this. We're adding them together. But now we have a this and this. Both of those probabilities must occur in order for him to say, I got in the second time around. And so we're now multiplying these two things together. Now, 20% is 1/5. So to be honest, just divide 85 by 5 and you've got it. 85 divided by 5, that's 50 plus 35, or 10 plus 7, 17%. Now, that one I did in my head. Does anyone need me to work that one out on how I got from 25% of 85 to get to that one? This was just kind of little X factor rules that I did there. So in the end, 15% plus 17% is answer choice C. 32% chance of David going to the Stern School of Business. Awesome. Okay, what a great probability question. It's now time to give you the mother of all probability questions. This one is not found in the manual, in part because I wrote this question. And I wrote this to highlight a whole bunch of issues with really mean probability questions. My guess is this is going to be at least a 750 level question. Were we to allow hundreds of students to be able to take it and kind of figure out its curve. And I'm only basing this guess off of how quickly students get this right and how quickly people miss this question. But let's do this one together and you'll start to see all of the critical thinking skills that we have just talked about, how we're going to bring it to bear on the meanest probability question of all time. Okay? So it says, well, actually, of all time, that's way too extreme. The meanest probability question that you will encounter on the GMAT. So Miranda has a fruit bowl containing a bunch of fruit. 5 bananas, 4 pineapples, 3 coconuts, 2 peaches, a kiwi, and half a watermelon. And now we're going for what are the odds? Well, there's great leverage that we're talking about a probability here. Of her randomly picking 3 fruits from the bowl and being able to make a pina colada made with a banana, coconut, and a pineapple. Now, ready? Let's start into this. A banana and a coconut and a pineapple. What are the chances of Miranda picking a banana out of the bowl, straight out of the gate? Nicely done, Gerald. There are 5 bananas, and if you were to add it up, 5 plus 4 plus 3 plus 2 plus 1 and half a watermelon, incidentally, half a watermelon is still an option. Makes sense? And so it's not 15.5. There are 16 options that Miranda can choose from. So 5 bananas. Now you're right, we are only picking 1 banana. But you see how even though we're only picking 1 banana, because there's 5 things that we could pick from that could work, then that top option is 5. 5 divided by 16. Now, let's figure out the chance of Miranda picking a coconut, assuming she's already picked a banana. What are the odds of her picking a coconut? Megan, great job. And Michelle right behind her. Rachel and Juan get, actually Juan's even simplifying it down, which is good too. So there's 3 coconuts, and now we have 15 possible options. Here we have a dependent probability. Because we've already picked the banana, we've reduced that as an option. All right, this one's really easy. Now, what are our chances of Miranda picking a pineapple? Now we're down to 4/14. Nicely done. If we were to simplify this down, notice 5 times 3 is 15. 4 divided by 16 is 1/4. We get 1 divided by 4 times 14, or 1 divided by 56. Now look at answer choice B. It's right there. That's also the wrong answer. It is the most picked answer on a problem like this, but it's not the correct answer. And the reason why is because of a GMAT Jiu-Jitsu technique that the test uses. It's both breaking your balance and leverage, depending on, first of all, it will break your balance if you don't know it, but it's leverage if you do. I like to call this 100% chance of order. Now, one, you're really, really close here. I like how you're thinking there. Whenever you have probability issues, you always have to take into consideration the order. So this is the chance of Miranda picking a banana and then a coconut and then a pineapple. It's going to be a different option if she picked, I don't know, let's say a coconut, a pineapple, and then a banana. Now, let's just walk through this. Coconut, pineapple, banana. Well, that would be 3/16 for the coconut. 3 coconuts, 16 options. And then we pick the pineapple. This would be 4/15, picking the pineapple. And then now picking the banana at the end, there would be 5 bananas divided by 14s. And those are the odds of her picking a coconut, pineapple, and then banana. But notice what happens. 3 times 5 is 15. 4 divided by 16 is 4. We're left with the same probability. Now, this doesn't mean the answer really is B. It means that we've got 2 separate scenarios. Each of them have the exact same odds. Now, the fact that they're the same isn't coincidental. We can use this to our advantage. And great job, those of you that spotted this. Notice pineapple, coconut, banana, coconut, pineapple, banana. We also have coconut, banana, pineapple. We've got banana, pineapple, coconut. We have pineapple, coconut, banana, and pineapple, banana, coconut. Sam's already identified exactly what's going on here. This is a permutation. 3 factorial different ways of arranging the fruits. 3 fruits, 3 spaces, 100% chance of order, and so we've got a permutation happening here. Now you're right, we're putting these in a blender and order doesn't matter in the end, but with probability you always have to consider the different orders, and so in the end this is going to be either this or this or. All of them will be the same, but because it's either this or this, we technically add them, but we're adding 156 to itself 6 times, or in other words, we're multiplying it by 3 factorial, 6 ways. The correct answer is 656, and that simplifies down to D, or 3/28. There, we have easily a 750 level probability question. You'll also notice we're going to introduce one more thing happening here. We like to call this combinatorics. Now, that is not a word any more than GeoGebra is, but it teaches a similar principle. Because probability and combinatorics are 2 branches of mathematics that are really just there to measure and calculate real-life scenarios. When you get into some tricky issues, sometimes you see combinations of them, where you might have a probability question that in the end requires you know the different ways of combining elements, a kind of a combinatorics thing. Don't be afraid of these. It just turns into a couple small problems and allows you to be able to get to the right answer. But the main reason why I wanted to show you this is that tactic right there. 100% chance of order for probability. Now that we've got our pina coladas all ready to go, any questions on this before we move on to the next question? There's a lot going on here, and I want to make sure everybody understands kind of what just happened. Anyone still wondering on something? Okay, looks like we don't have any questions, and if we do, I can always go back to the slide. But let's pick up, we see Elda. In fact, Elda, kudos to you. It looks like Jeff's already given them as well, but Elda's clearly read ahead. Elda, you understand the concept of a mirror strategy. Now, this is when you're dealing with complicated probability questions, especially those that have the leverage phrase, at least one. At least one is a lot of work. It's because it could happen once or twice or 3 times or 4 times or as many times it happens. But you think about the logical opposite of at least one, going all the way back to our very first lesson together. Remember that logical opposite game we played? That was not just a way to get you frustrated with Sesame Street's concept of opposites. Logical opposites show up all over the place. The chance of it never happening is easier to calculate than the chance of it happening at least once. Now, an inverse probability we get at a basic level. It's 100% chance minus minus that chance creates the inverse probability. For example, and this even goes back to our discussion on Vegas. The odds I looked this up and we discovered that the odds of winning at an average Vegas slot machine. Now, there are actually some casinos that have they even advertise a higher winning rate in their machines. But across the city, 6% is the chance of winning in a Vegas slot machine. Now, for those of you going, wait, awesome, that's amazing. Notice what this also means: that the odds of losing at an average Vegas slot machine are 94%. That's why the casinos are bright and shiny. It's because the house is going to win at these, at least in aggregate. Let me show you an example of a mirror problem. Here we have our 4 dice. They're obviously fair because welcome to the GMAT. And notice we also have them thrown simultaneously. We still have an order that's happening here, but I'm going to show you another way around the 100% chance of order that can be used especially for the inverse probability ideas. Okay, notice the leverage, at least one pair. As soon as you see that, you go, when I see at least one pair, then I'm going to use the mirror strategy. However, you're going to want to paint your target here. You want to do 1 minus the percentage, and that becomes your target. Can you see why? If you don't do this, the test is almost guaranteed to include the right answer to the wrong question, where you've calculated the inverse probability, and you don't take that one next step further and subtract that probability from 100% to get to the right answer. Now, here's how I'm going to avoid the 100% chance of order. We have 4 dice, and sure, they're thrown simultaneously, but we still have an order happening here. Okay, for dice number 1, I'm going to ask this question very carefully. What's my chance of rolling a number on dice number 1? Absolutely, Sam and Gerald, got it. I didn't ask what's my chance of rolling a specific number. My chance of rolling a number is 100%. Now, 6 out of 6 is technically right, but yeah, 100% chance. Chance of rolling a number, okay? Now that I got that number, okay, what's my chance of me rolling a different number on the second dice? I don't know what that number was. I don't care. Now we've got 5 out of 6 for that second dice. Yes, and now you can see how it's going to work. 3 is 4 out of 6. The fourth dice is going to be 3 out of 6. We still have the order here. One and then the other and then the other and then the other. But the way that I got around this, the 100% chance of order, is I went, I'm not talking about specific values. I'm not saying what's my chance of rolling a 1. And what's my chance of rolling a 1 again, and a 1 and again, and a 1 again, or a 2 or a 2. I'm just going, what's my chance of not rolling those things? And you can kind of step back and look at it a little bit more conceptually here. It's another way to get through that 100% chance of order idea. Now, notice how this simplifies. 6 out of 6 is obviously just 1. And 4 out of 6 is 2/3. 3 out of 6 is 1/2. We still have the 5 out of 6 there, but in the end, notice the 2's cancel, and we have 5/18. And if you pick answer choice B, the test got you because you didn't pay attention to the target that you painted. This is the inverse probability. You've got to subtract the 5/18 from 18/18, or 1, and you get 13/18, and the actual answer is E. Does it feel good? Now, you'll see I also categorize this problem as we call a lucky twins strategy. And let's spend a little bit of time on this concept of lucky twins. And the at least one sets up a very time-consuming thought process. If you had to actually calculate, I mean, think about it as 4 dice, and you have to go, wait, a 1 in the first one a second one. What about 1 in the third one in the fourth one? Those are all separate things you can need to add to. So your counterattack is taking the inverse, but now you need to make sure you answer the proper question. And the downside is the math will lead you to solve for a different fraction. And you're guaranteed, or almost certainly guaranteed, that different fraction will be a trap answer. So this is what we call lucky twins. Look at this problem. Do you see it? We have lucky twins is where you have 2 answer choices that sum to 100%. Now you can actually, while this is a trap of the test, you can also use this to your advantage. Let's say you're running out of time, or you just need to punt on the question. You're like, all right, I need to increase my chances of getting it right. And you see leverage like this, the at least one pair ideas. Well, look down at the answer choices. The psychology of the test is pretty predictable. And so if you had to pick an answer choice, well, narrow it down to lucky twins. And then you could look at the scenario and go, well, is it going to happen more often than not? At least one tends to happen pretty often. So I mean, that's going to be a higher of the 2, and you would pick answer choice E. If it doesn't seem to happen very often, you'd pick the lower of the 2. Now, the GMAT doesn't have to do this. So it's also possible that the real answer is D. Does that make sense? Which is that could work. And you could also see other issues. For example, what if instead of 1/2, it was actually like 1/3 or something? Now all of a sudden we have 2 lucky twins. 1/3 plus 2/3 is still equal to 1. However, you still might be able to look at the question and go, this is going to seem to happen pretty often, so I'm going to at least pick one of the higher of the 2 options. These are the lucky twins. It increases your luck in like punting on these hard questions. Okay, so let's step back all the way. Here is what you need to be able to go to Vegas. Notice that stats, combinatorics, and probability, it might seem hard, especially to you if this is your first exposure to it. But did you notice how the math itself really isn't hard? We're not doing nothing more complicated than adding and multiplying numbers. That's it. But you've got to think very conceptually about these questions. My confession, where I said I never knew the equations for combinatorics when I took my GMAT, should actually be an advantage to you. You can reason your way through these, and you have to be creating the equations that allow you to be able to solve for these as you look at the question. And so you've got to pay very special attention to the tiny details of the problem. Small changes in these scenarios create large differences of interpretation, and you'll never know you missed it because the test is going to anticipate those traps and cause you to miss the question. Now, as you're going through the problems, for homework problems for stats and combinatorics, pay attention to those answer choices that you pick thinking you're going to get them right, but you end up missing the question. That actually is, like if you got a number and it's there in the answer choices, then as part of your feedback loops analysis, that's when you take a deep breath, you slow down, you go, all right, why did I miss this? What was the details of the problem that caused me to go that wrong direction? Make a note of that in your error logs, and that will help you to be able to speed up your chances of getting these questions right in the end. Okay, now we're going to step even further back. Did you notice the patterns? The GMAT did some things to break your balance today. First of all, you see how the test tried to flex on you, making the answers or the questions look harder than they actually are. It's don't deviate. Man, standard deviation is designed to make the math look mean. Mean averages, where it baits you into thinking you've got to do a whole bunch of math when you don't. The mirror strategy, the at least one ideas, to get you thinking there's a lot of math involved when it's not. And statistical smokescreens shows up at all over the place, where it basically baits you into going, I need to calculate this statistic, when in fact you just need to understand the rules of the statistic and eliminate things that don't work. You also saw some great logical traps today where you make inaccurate assumptions about pieces of the question, or where you subconsciously insert extra information into the problem. Game, set, match was a beautiful logical trap. Remember, where you assume that the order in a set is the order of the set. It doesn't have to be. And then we also gave you some great leverage points here. There's some main content level jiu-jitsu here, and there's quite a few issues. This is where, just based off the problem, this isn't really critical thinking skills, it's just be aware of. When you've got probability, 100% chance of order. It's either this, or a simultaneous scenario, this and this. Those are how you know what you're going to do. And then combinatorics is just making sure you understand that on difficult probability questions, sometimes you might need to be thinking of combinatorics scenarios since you're just counting arrangements. And the next is just efficiency and strategy. This is how to leverage the structure of the problem to take down the problem. From visualizing the scenarios to understanding constraints, and then also using those lucky twins. And that is all the mathematics you need to be able to go to Vegas. So thank you for a phenomenal class. That was stats and combinatorics. Now, just a little reminder, by the way, Jeff's giving our shout out to our new GMAT Jiu-Jitsu Masters. Great job. Wow, we had a ton of people exceed their previous kudos averages. So you all deserve that. That is amazing. Next class, of course, is our final lesson. I can't believe this has gone so fast. And there's no skill builder for next time, so just show up and enjoy. We're going to talk the AWA, integrated reasoning, and then we're going to have our final advice section at the very end, where we're going to bring 13 years of experience of me getting people ready to get into top business programs to bear. We're going to talk about how to study for the exam, how to increase your chances of getting into business school when you apply. It's going to be a phenomenal discussion as we kind of have our climax at the end of last class. That was it. Again, thank you for a phenomenal class. Remember, Jeff and I will still be sticking around after today's class for as long as you need us. So please continue to ask those questions if there's still something nagging at you. Otherwise, we'll see you tomorrow for our grand finale. That was Stats and Combinatorics.